Consider a network of capacitors like this. This is simple enough. We have a branch here. There's another branch between A and B, junctions A and B, and they're in parallel. This are in series, these are in series, and this branch and this branch are in parallel. Simple. But suppose now we have a connection like this. It's something else altogether. This is not a simple series parallel circuit anymore. Now, if you consider any pair of junctions, you'll find that this one branch, fine, but in getting from this junction to this junction along this path, you encounter another junction. So it's not simple series parallel. How do we solve these kind of problems? How do we find the equivalent capacitance between A and B? One way is to assume a potential difference between A and B and find the potentials of these junctions in terms of the potential which we have assumed. Like, say, this is 0 volt, this is V volt. This is a very convenient way of assuming potential difference. You can choose one of the terminals or one of the junctions to be at 0 potential and the other at V. So we have a potential difference of V between A and B. Let the potential here be V1 and the potential here be V2. Let's say this capacitor is C1, this is C2, and this is C3, and this is C4, and this is C5. Now we know the potential difference of all the capacitors in terms of the assumed potentials, V1 and V2. The potential difference of this is, say, V minus V1. So charge on this plate would be C1 into V minus V1, positive. Let's assume V1 is less than V. And this will be minus C1 into V minus V1. That is the charge on this plate of the capacitor C1. Well, we'll assume that when it decreases as you go along, V1 is less than V and greater than 0. So the potential difference across this will be V1. V1 and 0, that will be V1. So the charge on this plate will be positive plus C2 into V1 minus 0. That is the potential difference of the capacitor. This is positive. This one, let's assume V1 is more than V2. We do not really know V1 is more than V2, or it could be the other way around. Depends on the network. Let's assume V1 is more than V2. So this plate will be positive, and the charge on that will be C5 into V1 minus V2. This should add up to 0, right? Because this, if you consider a small boundary here, well, around these three conductors, there is no flow of charge into that boundary from outside. So the charge on these three plates is all induced charge, so sum total would be 0. We could do something similar for this junction. So we have on this plate minus C3 into V minus V2, right? And then now we already assumed that V1 is more than V2, so this will be minus C5 into V1 minus V2. And this one will assume V2 is more than 0. V2 is positive, so plus C4 into V2 minus 0 minus C5 into V1 minus V2. Again, if you draw a boundary around these three conductors, there is no wire crossing that boundary, no charge flowing in or out of that. So sum total of charge on these three conductors must be 0. So you can solve these equations, treat V as a known quantity and solve for V1 and V2. So you'll end up with something like this. V1 is some A times V and V2 is some B times V. That is, we'll be able to solve for V1 and V2 in terms of V. A and B will have some C1, C2s, the capacitors. Now what is the equivalent capacitance? Imagine this is all a black box. You applied a potential difference of V, and the charge that flows in, if you know that charge that flows in flows onto these two plates. That is C1 into V minus V1 plus C3 into V minus V2. The charge that comes off through B will come from this conductor and this conductor. So you can go to that conductor. For example, the charge in this is minus C2V1. So charge C2V1 has left this. And this is C4V2 minus C4V2. That is C4V2 has left this. The charge flowing out through B is C2V1 and plus C4V2. And the ratio of charge, that's C2V1 plus C4V2, that is the charge that's flown out of B. It also be the charge that's flown in through A. But this looks a little tedious. C1 into V minus V1 plus C3 into V minus V2 looks a little tedious to write. That by V, that's the equivalent capacitance. So if you treat this as some kind of a black box in which capacitors, but we do not know how they are arranged. But imagine applying a potential between A and B and find the charge that flows through A. The ratio of that charge to potential difference is the equivalent capacitance between A and B. This is what we are saying. Say if this is the equivalent capacitor and if this potential difference is V, if I know this charge Q, what do we know here? Q is V into CE, right? So that's what we're doing. We are finding CE by saying, well, the charge that is flown in, where has it gone onto these two plates and where has it come out from B, and whatever charge that flows in must come out through B. So this is the technique for finding the equivalent capacitance in case when the capacitors are not in simple series or parallel. There is an alternative way of finding the equivalent capacitance. We don't assume potential difference between A and B. We'll assume some potential difference has been applied between A and B and the charge is flown through A onto these two conductors. These are the two conductors connected to A. So let this be Q1, let this be Q2. That is, we're going to assume Q's. A minus Q1 will be induced here. So Q1 leaves and a part of it, let's say Q3 goes here. Q1 leaves here, right? There will be minus Q1, Q1 leaves. Part of it Q3 goes there, so you'll have Q1 minus Q3 here. So assume labels for charges as many as necessary. And then this will be minus Q2, so this will be Q1 minus Q3 flowing in, and Q1 minus Q3 would have left this and Q2 would have left this. So the charge on this plate, I'll write it here, this one would be, well, Q2 has come in from here and Q1 minus Q3 is coming from here. So this is the charge on C4 on the left plate. So our interest is to find well, some relation between Q1s, and then we can get the potential between A and B in terms of this Q1. For example, VA minus Q1 by C1 will be the potential here, and then potential here would be V Q3 by C2 less, isn't it? This is V1 B. Will be Q3 by C2. So in terms of we're not assuming potential differences, so we don't need those V1s and V2s. So what is the potential between A and B? VA minus Q1 by C1 minus Q3 by C2 will be VB. That's the potential. So VA minus will be Q1 by C1 plus Q3 by C2. So we know the potential between A and B in terms of the assumed charges. Assume as many labels as necessary. If you have more junctions, you'll need more unknown charges. The rule you write for the potential difference is, if you start from here and go around the circuit and come back to that point, the sum of potential difference must be 0. So let's start from here. Along the conducting path, there will be no potential difference. Potential difference is only across the capacitor, and that will be minus Q2 by C3. If potential difference is negative, that is, there is a decrease, we'll put that as negative. This is positive and this is negative, so there's an increase. That will be an increase of Q1 minus Q3 by C5. That's an increase. And this again is an increase of Q1 by C1. So we're back to the starting point, so this sum must be 0. Algebraic sum of potential difference in a closed path, that's 0. We could do something similar here for this path. So that will be, if you go this way, that's negative, potential is decreasing. We assume that Q1 minus Q3 is positive. So Q1 minus Q3 by C5, the minus sign, that's a decrease. There's another decrease, that will be minus Q2 plus Q1 minus Q3 by C4. Then you're going back to this, so that's an increase, plus Q3 by C2, this adds up to 0. So we're going to solve for Q1, Q2, Q3 in terms of C's. You get, well, Q's related here. Now what is our equivalent capacitance? Equivalent capacitance will be charge that is flown in, Q1 plus Q2 by potential difference between A and B. So you can go this way, and that's potential difference of Q1 by C1 plus Q3 by C2. What is this? This is the potential difference between A and B. It looks tedious, but sometimes this works out well. So you need just Q1 and Q2 in terms of C's. Well, let's say treat, well, if you get Q3 in terms of Q2 and Q1 in terms of Q2, Q2 gets eliminated here. So treat one of them as known and solve for the other in terms of that. Say, solve for Q1 and Q2 in terms of Q3, say. Q1 in terms of Q3, some A times, say, some constant A which involves all these C's. The Q1 is some, I'll write it here. So you will solve, and this will be some A times, say, all those A times, you will get that in terms of Q3. Similarly, Q2, you will solve for B times Q3. So solve for Q1 and Q2 in terms of Q3 and substitute here for, say, Q3 or Q1 and Q2. A times Q3, B times Q3, A times Q3. So that Q3 gets eliminated and you're left with only C's. So C effective is known this way too. Doesn't seem simple, but it can be in some cases. As we work with some examples, you will understand that better. Consider a circuit like this. Between A and B, there are 3 equal capacitors. This will be a simple series branch, and equivalent capacitance will be C by 3, but that's not what we have. There's something like this. So it doesn't seem like a simple series parallel connection. That is, if you pick any pair of junctions, you have one branch, but the other branch leads to a junction. So let's go to our usual assumption of potentials and solve this problem. So we'll assume a potential difference V between A and B. And then we need to assume potentials at the junctions. For example, if I go to this junction, what is its potential? Interestingly, we have a conducting path to B, so there's no potential difference across this conducting wire, so this is 0. And again, this junction is connected to A through a conducting wire, so potential is V. So we know the potential difference in terms of what we assumed. We don't have any unknown potentials here. Now if this is 0 and this V, the charge in this will be CV, right? V and 0. This V and 0, this is plus CV, this is plus CV. So we know the charges in terms of this V. This is CV, CV, CV. So charge that is flown in through A would have gone onto this plate, some of it would have gone on here and branched out onto these 2 conductors. So sum total of charge on these 3 conductors is charge that is flown in, which is CV, CV and CV, 3 CV. That is charge that is flown in through A. That by the potential between A and B, that's the equivalent capacitance. So this is 3C. You could also have seen the charge here is minus CV, that is CV left this. This minus CV, CV has left this, so charge that is flown through this wire is 2 CV, and a charge of CV comes from this, because this is plus CV, this will be minus CV. CV has left this, 2 CV coming this way and CV coming this way will flow out through B as 3 CV. You can either look at, well, charge flowing in or charge flowing out by looking at the conductors connected, either entry point, this is the entry point for the charge, or the exit point. So this is the equivalent capacitance 3C. It doesn't look like simple series parallel, but actually it is parallel. If you redraw this a bit, you would see this as parallel. No need for redrawing, you could always do this. Consider another slightly more complicated circuit like this. All C's between A and B. So you could start with assuming a potential difference of V between A and B. Now if you go to the junction like say here, well, there is no simple connection to any other terminals where you already have assumed potential. This 0 and this V you assumed, right? So we need a new label. Let's say this is V1. And then if you go to this junction again, there is no simple connection between this junction to other junctions where potential has been assumed. So you do not know the potential here either. You can assume that to be V2 and solve. That's one way. Let's do that. Let's say we'll assume this to be V2. Now what's our logic? We will find the charge on the plates which are not connected to any, that is, if you imagine a boundary like this, we can isolate these three conductors. Similarly, if I imagine a boundary around 1, 2, these three plates, through these air gaps, through the gaps between those plates, mind you, there's an insulator between the plates, so no charge flows from one plate to the other. So if you consider these three, the charge on them must add up to 0. Same here, charge on these three must add up to 0. What is the charge on this? Let's assume V1 is less than V, so this will be C into V minus V1, and this will be minus C into V minus V1. That is charge on this. Let's assume V2 is less than V1, so this will be C into this one plus C into V1 minus V2. And then this one, this is 0, this is V1, so plus CV1, this is 0. And the other equation is for these plates, because there are two unknowns which you assume V1 and V2, treat V as unknown quantity. So this will be minus C into V1 minus V2. We assume V1 is more than V2. This is plus CV2, this one, and this is minus C into V minus V2. Right? This is V and this is V2. We're assuming V is more than V2, so this is plus C into V minus V2, and this minus C into V minus V2, and this is what we have. This adds up to 0. Solve for V1 and V2 in terms of V. Well, you can do that, and then you will find C1, V1 equals V by 2 and V2 equals V by 2. Solve that, simplify and solve. Treat V as a known quantity and solve for V1 and V2 in terms of V. Look at these equations. C gets eliminated, minus V here, right, that goes to the other side and becomes plus V. Treat V as a known quantity. This is plus V1, 2V1, 3V1, minus V2. Right? Same thing here, solve for this too. What do you get here? Again, we'll push V to the other side. This is V, this V goes that way. This is minus V1. Yes, minus V1. Plus V2, plus V2, plus V2, plus 3V2. Well, solve for V1 and V2 in terms of V. And once you do that, well, C effective would be, well, charge that is flown in. It's here on these plates, right? So, or you go here because 0 things become a little more convenient. This is minus CV2, so CV2 has left that plate. So, flowing through B, charge flowing through plus, this is V1, so this is 0. So, this is convenient that way. C1, V1 has left this. That by V. Since you can solve for V1 and V2 in terms of V here, you can get what you want there. So that's it. That's solution C effective in terms of C's. Let me solve this for you. We'll multiply this with 3 and add. So this will go away. 3V1, 9V2 we'll do what? Add, multiply with 3 and add. So this will be 8V2. This is 3 into 3, 9 minus V2 adding. So this is multiplied with 3V and plus V, that will be 4V. So V2 comes to V by 2. Substitute for V2 here, say V2 is V by 2, this will be 3V by 2. So V1 will be, this V1 goes that way, 3V by 2 minus V, that will be also V by 2. Solve for V1. So if you put that V1 and V2 here, V by 2, V gets eliminated. So this C by 2 plus C by 2, that is this V by 2, V gets cancelled, so V by 2, this is C. C effective is C. Interesting. In fact, you also could argue that if V1 is equal to V2, this capacitor doesn't store any charge. You can forget that. If V1 is equal to V2, this nice situation here because of the symmetry. V1 is equal to V2, this capacitor doesn't store any charge. So you can forget that this is junction. Nothing is flown this way, nothing is flown this way. So you then see this as one branch, this is another branch, because there is nothing that is flown in this way, though it's physically there. There is no flow of charge in that path. So this can be ignored. You can just forget that there. So this is one path to B and this is another path to B, which are in parallel. So C and C in series, C by 2, C and C in series, C by 2, C by 2, C by 2 in parallel, that's C. Interesting. Let's exploit the symmetry in this circuit and simplify it even further. We're assuming a potential difference between A and B. You assumed a potential V1 here, but when you go to the next junction, is it possible to assume maybe a potential there in terms of already known potentials? Like what is known here? The charge that flows in this way, because of the symmetry here, if these were unequal capacitors, you couldn't have said this. Because they're equal, the charge that flows this way should come out this way, which means the potential difference of this and this must be equal. So what is the potential difference of this? V minus V1. So this must be V minus V1. So if this is 0 and this V minus V1, this will be V minus V1. So you just assumed one label and potential of the other junction has come out in terms of the assumed label, already assumed label. So you only one unknown potential to solve for, say V1. Now do you solve for that? Charge on, say, these three plates must add up to 0. What is charge on this? This is V minus V1, right? So this would be a minus C into V minus V minus V1. This is V minus V1, this V, so potential difference is V minus V1. So this is together, right? And then what is the charge on this? Plus C into V minus V1. Charge on this. And this minus CV1. This adds up to 0. Solve for V1 in terms of V. I'll check. C goes away. There is V here, minus V here, plus V goes away, minus V, that goes to the other side, and that's V. And this is V1, minus V1, that is minus 2V1 and plus V1. So we'll get V1 is equal to, let's check this again. Simplify this and you'll get V1 is equal to V by 2. So you get this V gets cancelled, so this so minus V here, so V gets cancelled. This V1, this is yes, minus 2V1, so V minus 2V1 equals 0. That's what you're getting here. I hope you can see that. So V1 is V by 2. If V1 is V by 2, this is V minus 2, this is also V by 2. So you can either write the equations or realizing that these two are equal potentials. No charge on this capacitor, so forget that, remove that. So that will become simple series parallel arrangement. Interesting, right?